In this lesson, we're going to look at solving for time. And basically, we're going to start out, we've had our formulas that we've used for the past 2 lessons, and we're just going to make sure that we know them and write them down before. So this is a good time to pause the video. You have your formula sheet, but see how many of the formulas you can write down without using it. Okay, at this point, let's write them in so you can check and see how many you knew, and this will tell you which ones you need to study for your quiz on Wednesday. So this is the first one. Simple growth is P times 1 plus R to the T. Periodic compounding means that we get little pieces of the interest more often. So we bring in the variable N, that's how many times we compound usually it's per year, but whatever time period is picked for T. So we do divide up the interest, so R over N, and then we get it more often, so we use to the NT. For continuous compounding, and we still haven't looked at where E comes from, and we'll do that in two lessons. But for this one, we have P times E to the RT. So noticing on this one, the big thing is that we don't do 1 plus R, we just put the rate there without adding the 1. Half-life is P times 1/2 to the T over H, where H is the length of the half-life, and doubling time is P times 2 to the T over D, where D has the same function as the half-life. We just use a different variable for it because we're talking about doubling. So we're going to get into problems now. Our first step is to pick which formula to use. The first one says an investment of $300 is made at 3.6% yearly interest compounded continuously. So I am going to write down which formula goes with each of these first. So compounded continuously, we're going to use our PERT formula. Variables we have that P is 300. This gives us that R is 0.036 because we have 3.6% yearly interest, that's positive. And then time for the first problem is 10 years. So we're going to calculate this one. We're plugging in a 10 for time. So this is not necessary to write, but I'm going to write A of 10 since I'm plugging in 10 equals 300 E to the 0.036, plugging that in for R, and then time is 10. So in this problem, similar to what we've been doing for the past few days, everything we have on this side, including E, because we know E has a value, is numbers. So we can just type that directly in our calculator. And if we did, it doesn't say what to round to, but I'm going to round to the nearest dollar. That would give us $430. Now, the next question gets more into the topic for today. It says, algebraically determine the number of years it will take for the investment to, this should just say, be worth $800. Round to the nearest hundredth. So we're going back. Now we don't know the time. In the last problem, we had plugged in 10 for the time. We still have the same information for the P value and for the R value, and we're still using our PERT formula. But now we know what it's worth at the end. Its end value is 800, so I'm going to plug that in for A of T. So we have 800 equals 300 E to the 0.036 T. Now looking at this, whenever we have the variable and the exponent, we know that at some point we're going to have to go to log form because we know the log equals the exponent in log Benny. The first thing I need to do, though, is I need to remove the 300. So I'm going to divide both sides by 300. That is going to give me approximately 2.67. It's really 2.6 repeating. I'll keep that whole decimal in my calculator to use later. Now we have a base, an exponent, and a number. So now we're ready to go to log Benny form. So I take those numbers. I'm going to write the word log. My base is E. My number that it's equal to is 2.67, which I'm going to keep the whole decimal in my calculator, and my exponent is 0.036 T. Now, when I see this, it's fine to leave it like that, but I can also notice that I have log base E, and I could replace that with ln. So if you want to use your ln button, this means the same thing as log base E. If I type in ln or log base E of the 2.67 using the whole decimal, I get 0.98 approximately. And then I'm going to divide that by 0.036 to finish off the problem. That gives me a final answer to the nearest hundredth of 27.25. Looking at the next one, we're going to be working with a different formula. I'm just going to move the page down and erase some of the stuff that's in the way. The population of a town with 12,500 residents is decreasing at an exponential rate with a half-life of 17 years. Algebraically determine when the population of the town will reach 5,000 people to the nearest tenth of a year. So on this one, whenever I see half-life, and I also do not know what percent it is, that means we're definitely not working with one of our first three formulas, and in this case, we're working with half-life. So I'm going to write down that formula. A of t equals p times 1/2 to the t over h. Looking for values I have in this problem, my start value is 12,500. My half-life is 17. And in this case, this number is what a of t is going to equal to. That's our number at the end. So plugging those values in, I have 5,000 equals 12,500 times 1/2 to the t over 17. Now, I would suggest pausing the video here and solving this, seeing if you can get the correct answer to the nearest tenth of a year. Okay, so now that you've tried it, let's go through the work for that one. We're looking for bend form, but we have this number that's multiplied by 1/2, so first we have to get rid of that. So I divide by 12,500. That's going to give me 0.4 equals 1/2 to the t over 17. And then I'm going to put this in logarithmic form because I now have my base, exponent, and number. So that's going to give me log base 1/2, which we could use 0.5 for if we wanted to, of 0.4 equals t over 17, the exponent. When I type in this logarithm, that should give me approximately 1.32, keeping the whole decimal. And then lastly, we just multiply by 17, giving me a time of 22.5 years. At different times, I always want to do kind of like a check to make sure that makes sense. We started with 12,500. We're ending with 5,000. So I'm expecting it, if it had been half of 12,500, I would expect it to take the half-life of 17 years. It's a little bit less than that. Half of 12,500 would be 6,250. So 22.5 years is reasonable. Okay, moving on to the second page, I want you to try, and this numbering is off, the first exercise 3 on your own. But before you do that, I want you to just change the second one, exercise 4, just in case you're working ahead, because we're going to do a slightly different problem with that one. I'm going to cross out the second sentence. And I'm going to do, Lewis is going to invest in an account paying an annual interest rate of 1.8% compounded monthly. I'm going to write, if he invests $9,000, how long will it take for the account to double? To the nearest tenth of a year. Now, moving back up to the top one, I'm also going to say we're going to round to the nearest tenth on this one. I want you to pause the video and try this question on your own. Come back when you're ready. This one says a virus is spreading such that the number of people infected doubles every 4 days. 75 people are currently infected. How long will it take for 550 people to be infected? So looking at this, we definitely have a doubling formula. My doubling time is 4 days. I'm starting with 75 people, and my function's value after a certain amount of time we're going to look for is 550. So setting this up, I'm going to set this equation equal to 550. My start value is 75. The base of a doubling time formula is 2. And we have time over 4. This one's very similar once we get it set up to the half-life. So I'm going to divide by 75. That is going to give me approximately 7.33. Now I have Ben, I'm going to put it in log form. So we have log base 2 of 7.33 equals t over 4. Typing this into my calculator, I get 2.87. And then multiplying by 4, we get a time of 11.5 days. Looking back, we're working with days in this one versus years in some of the money ones. So now moving down to the next one. Basically on this one, you should, when we read this, Lewis is going to invest in an account paying an annual interest rate of 1.8% compounded monthly. So we see that we're working with our compounded periodically formula. Now, the only tricky thing about this is the formula looks complicated because we have the 1 plus r over n. I want you to try this one on your own, but as soon as I get 1 plus r over n, I'm just going to type in that part and just get that decimal and use that decimal throughout the problem, so I'm not looking at fractions. So go ahead and set this one up and then come back when you're done. Okay, so for this one we have our R value, and I'm going to write this down here. R is 0.018 because I made it a little messy by changing the problem. We're compounding monthly, so n equals 12. And we're starting with 9,000. And if we're doubling, our goal at the end is to have 18,000. So plugging in those values, we have 18,000 equals 9,000 times 1 plus 0.018 over 12 to the 12t. So as I said, the first thing we want to do is just get a decimal value for this. So it's just a little less to look at. Now, nicely on this one, it is exactly 1.0015. Sometimes you'll get a repeating decimal and you'll just have to highlight it in your calculator. So I'm going to divide by 9,000, giving me 2 equals 1.0015 to the 12t. Just cut that off so we can see it a little better. Now, I'm actually not going to put the next problem on the video. I'm just going to let you start on Delta Math. So I'm just going to go down here to finish this one. So now we have Ben form. So I put it in log Benny form. If I type in my logarithm, I'm going to get approximately 462.44. And when I divide by 12 to the nearest tenth, we said that's 38.5 years. So you can go ahead and work on the lesson 63 Delta Math homework. I made it super short. The biggest thing you need to be careful of is making sure that you're keeping the decimals and rounding to what they say, because it's very sad when you do a whole problem correctly and then you get it wrong on Delta Math because it's off by a couple hundredths.